Hello everyone. In the last video of determinant, we will discuss about adjoint of a matrix and how to find the adjoint of a matrix, and after that some of its properties. Look at there. Please remind that property. If A be a square matrix of order n, then A multiplied with its adjoint is equal to adjoint of A into A is equal to determinant of A into In, where In is a identity matrix of order, and this is one of the most important property that we studied in the last video. Okay, in this video we will discuss about inverse of a square matrix. We already discussed this topic in the videos of matrices. Okay, again I repeat here, a matrix, a square matrix A is said to be invertible if there exists a matrix B as of order A such that AB equal to BA is equal to identity matrix. That means a square matrix A is said to be invertible. That means the inverse of A exists if we find a matrix B such that A multiplied with B or B multiplied with A is equal to identity matrix. Here B is called inverse of A, that is A inverse is equal to B. Okay. In the videos of matrices we already discussed that how to find the inverse of a matrix by using elementary transformation. Okay. Look at an example here. If we take A is equal to 3, 10, 2, 7, a square matrix of order 2, and B is equal to 7 minus 10 and minus 2, 3. Here A into B is equal to 3, 10, 2, 7 multiplied with 7 minus 10 minus 2, 3. Here we get 1, 0, 0, 1. That means identity matrix of order 2. Similarly, BA is equal to 7 minus 10 minus 2, 3. B with A. We also find this product as an identity matrix. So here we get AB is equal to BA. Both are identity matrices. So here we say that A inverse is equal to what the matrix B, that means 7 minus 10 minus 2 and 3. Okay, let's see an important theorem here. What he said, a square matrix A is invertible, that means its inverse exists if and only if A is non-singular. That means he said that if a square matrix is invertible, then it must be non-singular, and in the reverse way he said that if a matrix A is non-singular, then it must be invertible. So we can prove this first in forward direction. Let A be an invertible matrix. Invertible matrix. So, and we show that it is non-singular. That means A is an invertible matrix given and we have to show that it is non-singular. Okay. So since A is invertible matrix, since A is invertible matrix, so by definition there exists a matrix B such that AB is equal to BA is equal to identity matrix. Is that it? Yeah. AB is equal to BA is equal to identity matrix. Now look at here. AB is equal to identity matrix. Now take determinant both sides. Determinant of product AB is equal to determinant of A into determinant of B, which is equal to determinant of identity matrix is equal to 1. So here we get the product of two numbers is 1. So neither of them must be 0. That implies, here we can imply that determinant of A not equal to 0. This implies, thus, since determinant of A not equal to 0, thus A is a non-singular matrix. Non-singular matrix. Okay. So in the forward direction we show that if a matrix A is invertible, then it must be non-singular matrix. In the reverse way, we have to show that if let A be a non-singular matrix, and we show that A is invertible. We show that A is invertible. Okay. So as we know that A into adjoint of A, which is equal to adjoint of A into A is equal to identity matrix, determinant of A into I. Since A is non-singular matrix, so its determinant must be not equal to 0. So divide the equation by determinant of A, we get A into adjoint of A, which is equal to 1 by determinant of A into adjoint of A into A, which is equal to I. Is not it? Since it is an scalar quantity, we can write it as A into 1 by determinant of A into adjoint A. Also 1 by determinant of A into adjoint A times A is equal to identity matrix. Isn't that it? Because 1 by determinant of A is an scalar quantity. By taking 1 by determinant of A is equal to adjoint of A, by taking 1 by determinant of A into adjoint of A is equal to B, we get AB is equal to BA is equal to identity matrix, which is the definition of a invertible matrix. This shows that A is invertible. So in this theorem we show that if a square matrix A is invertible, then it must be non-singular, and if a matrix A is non-singular, then it must have a inverse. That means it is invertible. Okay. What we get here? B is equal to 1 by determinant of A into adjoint of A. As you know that here V is inverse A, so replacing B by A inverse, we get A inverse is equal to 1 upon determinant of A times adjoint of A. This is most important formula. By using, we can easily find the inverse of a matrix. Okay. See a question. Find the inverse of the matrix A is equal to, what is the matrix? 3, 10, 2, 7. So here we find the inverse of matrix A. Look at the solution. Given A is equal to 3, 10, 2, 7. Therefore, determinant of A is equal to 3, 10, 2, 7, which is equal to 21 minus 20, which is equal to 1, which is not equal to 0. Since determinant not equal to 0, so A must be a non-singular matrix. That means since A is non-singular, so A is an invertible matrix. That means, or we can write that, so inverse of A exists. So now we can find the inverse of A by using this formula. For using this formula, we have to first find the adjoint of A. For adjoint, we have to first find the cofactor of matrix A. So cofactor of matrix A, that means C11, that means cofactor of element 3 is equal to 7, and C12, that means cofactor of 10 is equal to minus 2, and C21, that means cofactor of 2 is equal to minus 10, and C22, that means cofactor of 7 is equal to 3. Therefore, adjoint of A is equal to 7 minus 2 minus 10, 3, 8 transpose, which is equal to 7 minus 10 minus 2, 3. So the inverse is given by, so therefore A inverse is equal to 1 upon determinant of A into the adjoint of A. So here determinant of A is equal to 1, so this is 1 upon 1, and adjoint of A is equal to 7 minus 10 minus 2, 3. So it becomes 7 minus 10 minus 2, 3. So therefore A inverse we get 7 minus 10 minus 2, 3. So by using this formula, we can easily find the inverse of a matrix. This process is quite simple as of by using elementary operation. Okay, so this formula is most important to find the inverse of a matrix. Okay, so A inverse is equal to 1 by determinant of A into adjoint of A. Now we see some properties of inverse and adjoint of a matrix. Okay, first one is, if A and B are two invertible matrices, that means the inverse of both A and B are exist, then the matrix AB is also invertible and inverse of product AB is equal to B inverse into A inverse. That means inverse of AB is equal to B inverse into A inverse. Look at here, proof is not required for 12th class students. Okay. Next property is, this is also called reversal law. This is also called reversal law. Second property is, if A is invertible, then transpose of A, that means A transpose is also invertible. A transpose is also invertible, and the inverse of A transpose is equal to the transpose of A inverse. Transpose of A inverse. That means inverse of A transpose is equal to transpose of A inverse. Similarly, next property is, if A is non-singular matrix, A is non-singular matrix, non-singular square matrix of order n, then determinant of adjoint of A is equal to determinant of A to the power n minus 1, where n is the order of matrix A. Similarly, next one is adjoint of product AB is equal to adjoint of B into adjoint of A. This is also called reversal law for adjoint. Okay, that means adjoint of product AB is equal to adjoint of B into adjoint of A. And next property is, if A is a non-singular matrix, that means its determinant is non-zero, non-singular matrix, then determinant of A inverse is equal to 1 upon determinant of A. Determinant of A inverse is equal to 1 upon determinant of A. That is, determinant of A inverse is equal to determinant of A to the power minus 1, which is equal to 1 upon determinant of A. Okay. Next property is, A to the power K, inverse of A to the power K is equal to A inverse to the power K, where K is any positive integer. That means for any positive integer K, the inverse of A to the power K is equal to A inverse raised to power K. Okay. Let's see two questions here. First question is, if A equal to is a matrix, then find the value of determinant of A into determinant of adjoint A. Look at the solution of question 1. As you know that determinant of A into determinant of B is equal to determinant of A into B. So here it becomes determinant of A into adjoint A. Isn't that it? As we know that A into adjoint A gives determinant of A into identity matrix. Isn't that it? Here A into adjoint A gives determinant of A into identity matrix is of order SM to A, that means order 3. So here we get determinant of the matrix A 0 0 0, determinant of A 0 0 0, determinant of A. Isn't that it? Since determinant of A into I3 is equal to determinant of A into what is I3? 1 0 0 0 1 0 0 0 1. So it becomes determinant of A 0 0 0, determinant of A 0 0 0, determinant of A. So since it is a diagonal matrix, so its determinant is product of diagonal element, that means determinant A to the power Q. And since A is equal to A 0 0 0 A 0 0 0 A, so its determinant is equal to product of diagonal element, that means AQ. So it becomes A cube to the power Q, which is equal to A to the power 9. Okay. Let's see the second question. What it gives here: if A, B and C are n cross n square matrices and given determinant of A is equal to 2, determinant of B is equal to 3 and determinant C equal to 5, then find the value of determinant of A square B C inverse. Therefore, determinant of A square B C inverse. As we know that since determinant of A into B is equal to determinant of A into determinant of B, so here we can write it as determinant of A square into determinant of B into determinant of C inverse. We can also write it as determinant of A into determinant of A into determinant of B. And the last property we see that determinant of C inverse is equal to 1 upon determinant C. So now put the value of determinant A. What is determinant of A? 2. So it is 2 into 2 into determinant of B is equal to 3 into 1 upon determinant C is equal to 5. So it is 12 upon 5. So determinant of A square B C inverse is equal to 12 upon 5. Okay. In the next video, we will discuss about the system of linear equations. Okay. Thank you.